I work at ClickHouse. I lead the observability team there. And today I'm here to share a little bit about how we built ClickStack, the open source OTel, Open Telemetry native observability stack. I've been working on that with my team for the last few years, along with some other product teams altogether. But before diving into the ClickStack itself, how many of you heard of ClickHouse? Oh, wow. Okay, maybe we can skip that. Yeah, I just want everyone to be on the same page, what ClickHouse is, what we do, and what's all about. ClickHouse is a Columnar database that started back in 2009. It went into production in 2012. It was open sourced in 2016, and now fast forward to today, it's on the top of the rankings on database engines, on the analytical databases. Originally, ClickHouse was designed for the clickstream traffic. It's optimized for aggregations and filtering over a large amount of immutable data. ClickHouse is not great on mutations, but it does support it, and we did improve it over the years, so don't put a cross on it, on the mutations. But essentially, it was built and optimized for ingesting lots and lots and lots of data and making it available immediately after the ingestion. And turns out this is exactly what observability means, right? We have the constant flow of data and we want it to be ingested and we want it to be available right after it is ingested, not waiting for indexes to be propagated and all stuff like that. So what's ClickStack? ClickStack is the open source ClickHouse observability stack, opinionated. It's easy to use, end-to-end. It handles everything from RAM and session replay to logs and metrics and traces and everything altogether. It's composed of three components: Open Telemetry for ingestion layer, data collection and batching and preprocessing, ClickHouse for storage and querying, and HyperDX for the UI. HyperDX was acquired by ClickHouse about a year ago. Actually, a little bit less than that, but somewhere in the beginning of the year. Time flies fast, specifically to cover this layer that we were missing. This stack is Open Telemetry native and can be spun up in just minutes. There will be links in the end. You can try it yourself. Today, I'm going to talk a little bit about our journey on building this stack. So one of the key decisions in any observability stack is where to put all the data, as the data store that you pick fundamentally limits the scale and types of the problems you can answer. And for that, let's rewind the clock briefly, talk about some of the prior observability tools that were before. Starting with a humble grep, you can telnet its 70s or like logging to the mainframe and search logs on any individual server. Over time, as we get more servers, we need to centralize the logs from many servers into one centralized data store, and Splunk solved it to some extent. Evolving further, it went to the Elastic. It provided the ability to scale into the growing volume of logs that systems were producing. We got to the point where it was hard to figure out why something has gone wrong from looking into individual messages. And we needed to start building aggregations or its graphical representation, charts. Unfortunately, the search engines like Elastic, they were not great at doing analytics. So metrics databases popped up, like Graphit. As more servers got added and systems got more and more complex, the problem of cardinality came around and Prometheus was introduced to handle that. And then companies, again, needed to scale their systems further with databases, like aggregating from multiple regions altogether. And Thanos was born. And there was like a lot of optimizations. There's a Victoria Metrics I see here, which is a fantastic database for many telemetry signals, but metrics specifically. But increasingly complex workloads for observability meant that we constantly been looking for new data stores to handle the next generation expectations of volume, cardinality, and efficiency. And when we looked at this timeline, we weren't really satisfied by the constraints imposed by these data stores. Let's talk about it. Let's talk about search. So Elasticsearch is one of the classic databases for the log search, and there's a number of databases like it. Elasticsearch has brought inverted indices, the full text search into observability space, essentially democratized log indexing and making large-scale search more accessible. These have some attractive properties and have popularized the idea of searching your way through logs, like needle in a haystack queries and pattern matching. And it's really fantastic for that, even today. The search syntax is intuitive and fast, supports aggregations, we have Kibana stack, you can plot charts on it, but as powerful as they come with limitations. When you zoom out, the cracks start to show. They're not optimized, the search engines, they're not optimized for extremely high write rates, certainly not gigabytes per second, without throwing a huge amount of hardware, throwing a huge amount of compute. It's tricky to make it work. Inverted index comes with trade-offs, and the size of the inverted index is one of them. You are naturally limited, but the message that you store is naturally limited in size. The more you index, the more storage it gets, the more compute you need, the more memory you need. It's not great. And aggregations are needed for observability, and and you can tune them to be somewhat cost efficient, but fundamentally they struggle with high cardinality data. And you need to start introducing aggregations. So aggregations, metrics, right? So we could use search engines for logs and maybe time series database to overcome the limitations, specifically the aggregations part. And these aim to address the challenge of search databases when it comes to the aggregation-heavy workload specific. We could keep search databases like Elastic for logs, offload metrics into time series system, Prometheus, for instance, for more efficient aggregation and pre-aggregate the data. And on the plus side, they're cost efficient for it. They compress data really well. They're much stronger provide much stronger basis for aggregations, at least until you run into high cardinality data. And at that point, the storage model starts to struggle and we start hitting limitations, cardinality. They also don't really support the kind of exploratory workloads that search was good at, like when you can just dive into the logs and see what was happening around it, like time context, what happened before. Its model is pretty fine. You have the preset labels, and that's it. To deal with cardinality, people pre-aggregate safe resources, but again, the cost of the fidelity, and that makes the root cause analysis more difficult. So while metric stores helped address one problem, we end up with a fragmented picture. Now we have logs in one database, metrics in another database, instead of like single store where we have the full picture on all the fidelity levels we are looking for in a single data store. Can we avoid it? What if we didn't have to make these trade-offs? Logs in one system, metrics in another system, each optimized for a single access pattern. What if we could have our cake, but also we can eat it too? The ideal data store would be cost efficient while supporting both fast search, fast aggregations, even at high cardinality. It would scale without compromise. And in today's world, it would lean heavily on cheap object storage for bottomless retention, with local disk acting more like a cache. And that kind of architecture changes also let us keep everything while rethinking how we're also thinking about retention. Especially if we had high compression on top of it, long retention times become realistic at lower cost. There's actually a lot of properties we wanted in ideal observability data store. I highlighted just some of them, some of the important ones. First, resource efficiency with high compression for the petabyte scale use cases. At the scales we're talking about, the system had to handle tens of gigabytes per second of insert and do it reliably. It also needed to deliver strong aggregation performance for powering dashboards and visualizations without falling over when faced high cardinality data. We were looking for an expressive query language that is with strong analytical function. This is one area where Splunk really shined compared to Elastic. And we need indexes too. Sometimes full text search is the right answer, but we also need the option to turn it on or turn it off, or do it for some subset of data. We wanted a flexibility around schema so that we can support arbitrarily structured wide events performantly like Elastic does, while also allowing our users to dynamically extract, transform, and parse data at query time like Splunk. And finally, the scalability today means leaning on the object storage, again, using the local disk as a cache. And we wanted it to be open source. We took a look around what other companies were doing and saw the companies like Netflix and Anthropic they all looking towards the Columnar databases for their next generation observability platform. And surprisingly, it was ClickHouse that they were looking at. There's some links on the case studies and the talks that Netflix and Anthropic was doing about how they adopted the ClickHouse for the observability platforms internally. And when you start digging into the Columnar data stores, disregarding specifically the ClickHouse, it becomes clear why they're so great for observability in general. Let's talk about going Columnar. Before we get into why Columnar storage works so well, let's look at its core properties. So the easiest way to understand is to contrast to it the row-based storage as used in databases like Postgres. Instead of storing full rows together, columnar storage writes data column by column. That makes the layout on disk much narrower, and it's much more efficient for analytics if you're not operating with a full data set. If you're not doing a select star, you're doing to select just some columns, you're just going to get the columns you want. We can also order the data by specific columns. In this specific example, Stack Overflow post, it's a Stack Overflow data store, they're ordered first by post type and then by creation date. That ordering gives us a natural way, here we go, yeah. That ordering gives us a natural way to filter and scan only the ranges we care about, but also provides other benefits. We can apply codecs on top of that individually for every single column, which shrink the number of bits needed to represent the values, because we have a limited data set in this column, and we know that exactly the type of that column is, we can fine-tune it. Combine it with a general purpose compression, like Z standard, and you end up with a very high compression ratios. And the ordering here is also important because it helps us to align adjacent values to each other on the disk. But the real magic is how Columnar data stores query the data, how they read it. When you run a query, the engine only reads the columns you actually need for your filters and selects. That slashes IO. And because the data is tightly packed in a line, the execution can be parallelized. And this is one of the biggest advantages of it, of the columnar orientation, is vectorized execution. Because the data is stored in blocks by column, we can read just columns we need, process them in parallel, and that means the ranges of data can be distributed across all the CPU cores in the box because it's sorted, with each core filtering and aggregating the data independently. And those partial results then can get merged together before the final sort, and then applying like the limits, the aggregations, and return the result. And this doesn't just happen at the node level. You can push this out across a cluster where aggregations are shared and merged at the coordinator node. So what does it mean in practice? It means very fast aggregations. You can massively parallelize it. You can massively parallelize the execution, the query execution. It's all super fast. Because we store data on disk by specific keys and we sort them by these keys. And in this example, by post ID and the creation date, we can build a primary index which is sparse. What does it mean? It means that you don't need to have an index to track every row. You can split it in granules, that's what we call it in ClickHouse, and store just the first value of a block. Because you have ordering, you can figure out where you need to go. You need to go before that, you need to go after that. This index can be megabytes, potentially for the petabytes data sets. And in ClickHouse, we have primary key entry in the sparse index by roughly 8,000 rows. It's exactly 8,192, but this is tunable and it can be also adaptive depending on your data. How can we exploit this? When we run the range query, the database only needs to scan the index, figure out which blocks could contain the values we're looking for, and skip the rest. That means filtering becomes incredibly efficient. Instead of scanning the entire data set, we can just get the blocks that matter, or granules that matter, and avoid touching the irrelevant data altogether. And besides that, in Columnar data stores and the ClickHouse specifically, there's also other really powerful indexes that you can choose to tune in a similar fashion. A min-max index, a Bloom filter index. But they're called skip indexes, and their purpose is not to find data. The purpose is to let you know that this data you don't need. And it's an interesting concept that was for many of our customers that I'm working with, requires some time to adapt, that you use index not to select the data directly, but throw it away. But once you get there, you're in it forever. Here's an illustration of that. And because it's a columnar data store, you can have lots of columns, right? You can have 100, you can have 1,000, you can have 10,000 columns. And you can specify what we call like a wide structured events. It's a really neat concept that allows for arbitrary properties to be stored in the columnar database. In ClickHouse, that's called a JSON data type. Historically, the columnar databases weren't great at handling schema on write for semi-structured data. Like schemas are defined ahead of, because your schema is fixed, it's hard-coded. But with that, you can store the semi-structured data. The idea is simple. You insert in a JSON document, it has a different mapping of the keys to key types from one row to another. And the database can infer the schema at the insert time and dynamically choose to represent those fields as columns. And when you encounter a key of a different type, what do? You create another column. That's all. And in the records where it was of another type, there's just going to be a null value. And that works and that scales. And that means that you get all the same benefits of querying JSON as you do like with the structured data, fast filters, aggregations, compression, without having to predefine every possible key. At the cost, of course, there's always a trade-off of the heavier ingestion. You spend more compute at the ingestion time because you need to parse it out. You need to figure out if you already have the columns created of the specific type, create them if they're not there, or just write it if it's already there. And that's huge for observability. The data this environment generates is highly dynamic and unpredictable, and being able to just ingest JSON without the upfront schema design, it removes a lot of friction and lets teams focus on the data and not on the plumbing, like thinking about how to model their observability data. You can just get the JSON and the database is going to do it for you. One other point is worth calling out. Because columnar databases are strongly typed, they don't just infer a type once. I just talked about it, but this is a representation of it on the screen. We just create, like when we encounter a key with a type that was not there before in the document, we just create a column for it. And the final place from the storage perspective that we're looking for is the object store on the database side. The columnar stores like ClickHouse are a natural fit. The writes are immutable. I mean, you can do mutation and you can update the values in ClickHouse, but that it requires it basically delete and then insert. So the data, when at rest, it is immutable, and it's a perfect match for using the object store here. And once the data is there, we can scale the compute separately from the storage. We can scale it horizontally, we can scale it vertically without duplicating the data set and needing to re-replicate everything between the nodes. So what we can do here is separate the compute from storage. And every query just reads from the same copy that is reliably stored in the object storage. That unlocks low cost, long-term retention, and also, again, lets us separate the read and write paths. Writes can flow continuously into the storage without the disruption. Read side can stay small most of the time and only scale up when the investigations on the heavy workloads that demand it. So we get scalability, we get cost efficiency, we get flexibility, all from pairing Columnar Store with the object storage. So let's summarize why Columnar Store makes sense to build ClickStack and why they should power every observability solution. First, the column orientation gives us great compression and assists with efficient reading. Allows us to scale to petabytes while remaining cost efficient. Inherently fast at aggregations because everything is stored by the column and we can work and the querying can be vectorized and parallelized across the nodes. We get efficient filtering on specific columns, all designed to narrow the data quickly. And I don't have time here now to cover in depth fast write It's like a whole thing about ClickHouse, how ClickHouse writes data. But trust me on that. More recently, we also got a flexibility around schema as discussed with the support of JSON, the schema on read and schema on write. And finally, most Columnar stores are the foundation of an OLAP database, which exposes SQL. SQL gives us the expressive query language we need with rich analytical functions, flexible filtering foundation that almost every team already knows how to use. It's one of the most popular query languages in the world. Even if your observability frontend does not expose SQL directly, it's still a solid base to build on. You can build a transpiler on top of it. It's all doable. Now, the next question, the next layer, why Open Telemetry? It's open. It's the industry standard de facto, standardized, the observability data collection. It gives us one consistent way to handle all the types of telemetry signals, like logs, metrics, and traces, without having to reinvent the wheel. And while the decision itself was simple, it was foundational for how we designed ClickStack. Open Telemetry also comes with rich SDKs across the languages. Instrumentation of your code is much easier. And we're an open source company. It was important for us to stay open, practice what we preach, like no lock-in, no proprietary agent. You can get the auto collector and get it running. And on top of that, Open Telemetry has a very big community. It was a huge factor for us. It means faster progress, better tooling, ecosystem that we can contribute to, and ecosystem that we can benefit from. It was an obvious choice for us to pick the Open Telemetry. But while ClickStack is Open Telemetry native, it isn't limited to OTel. We support any schema that can be represented as a row with labels and metrics. Open Telemetry is very opinionated about the data store-backed schema. There's like a set of exporters that essentially create it for you. Part of it is semi-structured. Yes, there's log attributes, there's resource attributes associated with every single event, but it still limits it. We don't have this limitation with ClickStack. ClickStack can work with any schema that can be represented as a row with labels and metrics. You may hear the term wide events. So these are structured events that unify logs and traces into a single record. Essentially, it's like labels alongside metrics. They're designed for high cardinality observability at scale, which makes them a natural fit for Columnar databases like ClickHouse. And the term is getting traction among observability practitioners as they less accustomed to just stuffing features into a metric and store it as a single row. Inherently, this felt like data duplication, but for ClickHouse, this data compresses really well. I would say that for this schema, the compression ratio would be something around 50 times or 70 times. So you can just store it, and it's backed by the object store. It's cheap. For those with the data or data warehousing background, this model may feel familiar. To expose this data in ClickHouse, you simply configure it as a log source. We treat it as logs with metrics kind of thing, requiring just a timestamp and just some columns to render that you can filter on. So we talked about storage, we talked about ingestion. Now let's talk about what developer sees, what the developer experience. So we wanted to build a dedicated interface because we wanted better usability. The reason we wanted a dedicated interface, it really comes down to usability. Alternative, of course, something like Grafana, it's extremely powerful, still puts a lot of burden on users to write SQL. You need to know what you're looking for, and you need to be able to express what you're looking for in SQL to use the explore mode or to build the dashboards. Yes, there's a connector to ClickHouse, but is it a good experience? I don't know. I would not recommend, although I use it, but I work at ClickHouse. SQL is fantastic for deep analysis. It's not the right fit for ad hoc investigations. Even in ClickHouse, if you write a query the wrong way, the analyzer will try to do its best, but doesn't always choose the most efficient path, and it's nuanced how you query around the indexes and how to optimize the queries. So SQL is a great foundation. We felt developers needed an interface that is purposely built for observability, that is focused around observability, around the ad hoc investigations, with ability to transform the ad hoc investigation into the dashboard experience seamlessly. And we didn't want you to become a SQL expert first before doing that. We wanted to hide complexity. An example of this is our heavy investment into centering our language, query language, around Lucene. That means users can come and type error, and they're going to get all the errors. Or they type like user something blah blah and get the user that they were looking for. And no crazy languages to learn. It is very similar to what you are getting in the Elastic. It was one of the foundational things that we had to build, and we invested a lot of time and effort in it. I really like it. I really enjoy it. On top of that, we made sure that even when you type in a query, there is an explainer panel that actually shows you what you will be, that translates the Lucene syntax into the human readable format. So you can understand how the parser is interpreting your query, and where you can double check if there's some errors, or it is going to filter what you want it to filter on. And that also helped dramatically. It reduced the number of questions from users by the order of magnitude. But for those who really want to get all the power of SQL, we did leave the possibility to query in SQL. I don't know if there's this thing works. It doesn't. You can switch here between the Lucene syntax and the SQL syntax on the UI, and you can just use whatever aggregations you want. You can use everything that your database, in this case ClickHouse, provides. You can do it. And likewise for charting, going from the ad hoc investigation experience to the charting is very simple. It uses the same syntax. Expose, it's a Kibana experience. Like, we expose very simple chart builders. They abstract away SQL, but give you the opportunity to use it if you need to, and focus specifically on what you filtered. Focus around what you need to look for rather than how to write the query to get it to it. But also, fast observability does need optimizations that runs database deep, and we embedded it into a product and hidden all this complexity from the end user. Let's say when you build up your table indexes, there are happy paths that you really want to drive user towards. One example of this by default, when the user types a word, it will force a token search or a whole word search. Rarely that does fail, but if it does, we make it pretty clear in app that wrapping your word in stars will do a substring search. And the English explainer that we have also makes it obvious what's happening when you're doing either one. That goes across the rest of the app as well, where we encourage exact property value matches, which can take advantage of the additional secondary indices by defaulting over substring property search. And the schema exploration is automatic. The schema inference is automatic. You just specify your table, it analyzes the schema of your table, and makes these adjustments for you, makes these recommendations for you based on what indexes you have set up, what primary key have you chosen, and things like that. It was really important for us to make sure that UI understands the database. And what I mean by that is that the interface can just be pretty layer on top. It has to be aware how the database is structured. What is your data schema? How to generate the effective queries for that. Otherwise, you're wasting lots of performance and you're going to get a bad experience. For instance, as I mentioned, we analyze the underlying primary key index that is in place in table, and we apply some optimizations to the queries to make them more efficient while still providing and exposing this simple Lucene style interface. Another example, how we handle the result listings. So when a user scrolls through logs over a really wide time range, the naive approach would be to fire one massive query and just wait for the results to come back and just visualize it, and that's it, right? That's painful. If the time range is really wide, it can take lots of time. So it puts big load on the database, and you're waiting for the results to come back longer than you should. Instead of that, we break this request into chunks, and the UI loads data asynchronously, pulling back smaller ranges at a time, and again, coming back to the data store. It can be parallelized. It can be executed on different nodes. The data does not belong to a single compute node. The compute nodes and the storage is completely separated, and that gives much better performance and much better speed. So again, the UI, not just a layer on top. It's actively working with database. It understands your schema. It understands what you're trying to ask, and sometimes tries to show you the better path to get to where you wanted to. So, to wrap it all up, When we built ClickStack, the foundational decision was to use columnar-oriented store. Of course, it's ClickHouse. That decision actually came even before we started working on the HyperDX, and it's one we continue to believe was the right one. Columnar databases are the foundation of the future for observability. Whether it's ClickHouse, it's Pinot, it's Druid, they're all capable of powering these kinds of workloads. And SQL sits on top of that as a lingua franca. It's unmatched for expressiveness when you need to go beyond the basic search. But building UI is where things get tricky. If you want performance, you can't just layer a generic interface on top. You need a UI that really understands your database. It really understands the database optimizer, the schema, how to generate the efficient queries for your workflows users care about. And that's the challenge that we're still working on as we evolve ClickStack, making UI smarter so it continues to deliver the best possible experience on top of very powerful foundation of ClickHouse and Open Telemetry. Thank you. Here's some links. We have a public demo that you can just take a look. It's like a playground. And there's a docs on how to get started with it. So give it a look, give it a try.